Hi, for those you don't know me, my name is Nicklawsky. I'm a biostatistician with the Biostatistics and Bioinformatics Shared Resource at the Cancer Center, if you're familiar with that. This is going to be the third lecture in a series that we've been putting on discussing novel phase 1 trial design. So we're hoping to convince you that there are better options than the regular 3+3 design out there. Last week, my colleague, Elise Staley, presented on the model-assisted Boyne design. Prior to that, I presented on just some of the other options in the 3+3 design that exist out there. Both these lectures are on our YouTube page if you go to our website, and if you'd like to, if you haven't seen them. This also will be posted to our webpage, so if you'd like to go back and review it, that will be available. So today I'm going to talk about 3 related model-assisted designs to the Boyne, the MTPI, the MTPI2, and keyboard. I'm going to spend the bulk of my time on the keyboard, and you'll see why in a sec, and just briefly talk about the MTPI2. So first, just a quick reminder. So what we're doing in this lecture series, we're talking about phase 1 trial designs. So these are restricted to phase 1. And just keep that in mind, where in a phase 1 design, we're specifically talking about looking for whether the drug is safe. We're going to be just talking today about model-assisted designs. If you remember in my first talk, there are generally 3 classes of designs. There's algorithmic approaches like 3+3 and rolling 6. There's these model-based designs, such as the CRM, which will be a talk next week. And then there's these model-assisted designs, which my colleague Elise had talked about last week, the Boyne, and then today I'll be talking about the MTPI and keyboard. So as you can see, these model-assisted designs are a relatively new phenomenon. And as I mentioned in my first lecture, this was in response to these model-based approaches, the CRM, you can see coming right after the 3+3, just being a little bit hard to implement in terms of having to have a lot back and forth between the PI and biostatistician. They're a little bit more like a black box design, whereas these model-assisted designs are really nice because they're very familiar to the 3+3 in that you can basically have a decision table pre-tabulated before you even begin, but they're more powerful than the 3+3, which I'm hoping to convince you of today. Once again, like I said, the major benefit of these model-assisted designs is you can pre-tabulate your de-escalation, dose escalation rules prior to the onset of the trial. Unlike the model-assisted designs, such as the model-based designs, such as CRM that we'll be talking about next week, we're only using local data, so we're not pre-specifying a model or anything. So the design itself operates specifically on what we're seeing during the course of the trial. Like I had said, that there's been many papers that have been written specifically talking about how superior these designs are in terms of identifying the MTD, allocation of patients to the MTD, and risk of overdosing relative to the 3+3 design. So we really advocate the use of these model-assisted designs. So first, let's talk about the MTPI, which was kind of the one that kicked off this whole model-assisted craze. So the MTPI, its acronym, it stands for Modified Toxicity Property Interval Design. It's a pretty trivial design to implement, although the underlying statistical theory itself is a little bit complex. I won't get too much into that. I'll just kind of go over the fundamentals of this design. It's pretty transparent because, like I said, you can see all these decisions before the trials even started. So essentially, when you're creating the MTPI, you're going to define 3 dosing intervals. So for example, we can say we have a target DLT rate or a dose toxicity, limiting toxicity rate of 20% or 0.2. So what we're going to do is we're going to define an equivalence interval, which will be what we're hoping to hit, which in this case we're choosing about 0.15 to 0.25. And then on either side of it, we're just going to have 2 large intervals that are either underdosing or overdosing. So in this case, our underdosing interval will be 0 to 0.15. Our overdosing interval will be 0.25 to 1. So as with like the 3+3 design, what we're doing is we're assuming that our toxicity probability of the drug will increase with the dose level. So we want to be able to determine when we think a dose is too toxic, with being the logic being the best dose is the one with the most that's most potent without the excessive toxicity, which is our MTB. So now that we have these 3 intervals, which is the reason that we can say overdosing is the upper one, underdosing is the lower one. Like I said, because that monotonic relationship between our toxicity and the potency of the drug. So just to note, the actual selection of our interval doesn't actually affect the complexity of our trial, and it can be any width for that equivalence interval. However, when you're trying to make your decision to do that, the lower bound should be whatever the clinician, or if you are the clinician, whatever you feel comfortable is using to treat future patients without escalating the dose. Whereas our upper bound should be what you feel comfortable using to treat future patients without de-escalation. So now that we have these intervals, how are we going to make our decisions? Well, it's based on the unit probability mass, or UPM for short, of these 3 intervals. Where the UPM is the posterior probability, if you're familiar with Bayesian statistics, basically our probability after we've observed the data of the interval divided by the length. So essentially what we're doing is considering the UPM to be the average probability density of the interval. And this is a lot easier to understand if you see it visually. So here, looking at this figure, we can see our equivalence interval right here, defined. Sorry, I know my mouse is on the screen. It's right between 0.2 and 0.4, and then we have the underdosing on the left there between 0 and 0.25, and the overdosing interval between like 0.35 and 1. So in this, so what we're going to do is simply, if the UPM after we've observed the data has the largest interval in the underdosing area, we're going to escalate. If the UPM of the overdosing interval is the largest, we're going to de-escalate, and then we'll remain if the UPM of the proper dosing interval is the largest. So for example, in this figure, what we're doing is, well, we're saying that for the entire range of the possible values of the probability of toxicity, we believe that the dose we are currently at has a density distribution where the largest area is proper dosing. So we're going to choose to remain. And I know just looking at the figure, it doesn't exactly look like that, but I promise if you actually calculated it out, it would be that way. But that's essentially what we're doing when we're applying these rules. And like I said, the underlying mathematics is slightly more complex than just calculating this based on size. But I didn't want to go too much into the weeds. because it can get pretty theoretical. But essentially, like I was saying, the idea is that we're determining where the results are from a dose. Say we are based on our previously defined dosing framework in terms of specifying those intervals and everything. So a couple other things with the MTPI, we're going to implement some safety rules to prevent dosing at an overly toxic level, and as well as terminating the trial early when the first dose is too toxic. So for instance, early termination, if the first dose has been used to treat patients and the probability of it being more toxic than the target toxicity is greater than a set percent, usually we choose 95%, we're going to terminate the trial. So we're going to end that early. And then dose exclusion, if there's a decision to escalate, but the probability of that dose being higher than the target toxicity is greater than a set percent, once again, typically 95%, then we're going to exclude that dose and remain at the current dose. So like I said, these are really crucial things that help make the trial not continue if a dose has just been found to be too toxic immediately, as well as not to treat at doses that have been found to have a high probability of being too toxic to begin with. So once we've gone through the entire trial, escalating and de-escalating, following our dosing decisions with the UPM, what we're going to do is take the dose with the smallest difference between the estimated toxicity and the target toxicity based off of our results, for which the probability of it being more toxic than the target toxicity is less than a set percent, usually 95%, and select that at the MTD. So it's fairly simple. We don't have to do anything. There doesn't have to be back and forth necessarily between the clinician and the biostatistician until the end of the trial, when we just look at the data and we calculate what the MTD needs to be. So the design seems pretty straightforward. However, the MTPI does have some downsides. Some of you might have already noticed that there's an issue, which is it's very dependent on the selection of our intervals. So you can see you can really influence your decision-making just on the basis of how large you choose those intervals to be, which often makes MTPI too aggressive. So for instance, especially compared to the 3+3. So for instance, I have a table here showing if we're looking at a situation of either a target toxicity of 20% or 30%, we can see, I know it's not highlighted super well, but if we're talking about having just a situation where we have two patients experiencing a DLT, with the 3+3, we're going to de-escalate. We see that being too toxic. Whereas with the MTPI, we're choosing to stay, which makes this slightly more aggressive. Same thing with if we're looking at a target toxicity of 30% in these decision-making framework, we can see that the 3+3 is choosing to de-escalate when there's about 3 of 6 patients with a DLT, 50%, whereas the MTPI is choosing to stay, which, you know, it just looking at that on face value, that's not correct. That shouldn't happen. Maybe statistically it seems to work validly, but in practice, that's not something we want to be doing. It's pretty risky. And the reason for this is because UPM that itself cannot appropriately quantify the evidence of overdosing. It's non-proportionally weighting the evidence of underdosing, proper dosing, due to the different lengths of the 3 intervals. So usually the overdosing interval, just by nature of our selection of our target toxicity, we want it to be low. That overdosing interval is typically going to be the longest. So we have a bit of a bias to suppress the evidence of overdosing. So I did some of the math here, but you can see with these intervals, say we have an interval of 0 to 0.17 for underdosing. For our equivalence interval, we have 0.17 to 0.23, and then our overdosing interval is 0.23 to 1. So at some point, our posterior probability of these intervals is going to be 0.01 for underdosing, 0.09 for target toxicity, and 0.9 for overdosing. So the 90% for overdosing, but the UPM for the proper will still be the largest, just based off these calculations. You can see 0.09 divided by 0.23 minus 0.17 is 1.5, whereas 0.9 over 1 minus 0.23 is 1.17. So we're probably overdosing, but our design itself, the UPM, it's telling us that we need to stay, which we don't want to be doing. The other kind of deficiency with the MTPI is similar to the 3+3. The sample size isn't fixed, so often it's just too small to get a really accurate estimate of our MTD, which isn't ideal. So why would I start with this design with all these kind of bad caveats to it? It doesn't seem to do much better than the 3+3. Well, the reason is the thinking for this design naturally led to this next design I'm going to present, the keyboard. And even though I mentioned I'm going to talk about the MTPI2, it was a little misleading because fundamentally the MTPI2 tried to do some things to address the issues with the MTPI, but it's very similar to how the keyboard operates. And I think the keyboard is a better design, a little bit easier to understand, pretty easy in principle. So I'm going to focus on that instead. So the keyboard design, like I said, it's meant to address the deficiencies in the MTPI. So we're going to do things to not be overly risky, essentially. And relative to the 3+3, we're still going to have higher accuracy and so on. It's a Bayesian model design relying on a posterior distribution of toxicity probability to guide decision-making. Similar to the MTPI, we're making our decisions based off this posterior probability. However, it's going to differ from the MTPI because rather than just looking at these three intervals, it's a keyboard. We're going to be looking at everything as an equally spaced interval. So we're trying to eliminate the fact that that size really influences our decision making. So in practice, how does that work, or what's the framework look like? So first thing we're going to do, same as the MTPI, is we're going to identify our target proper dosing interval. So I have an example here I just mocked up. Say that we're trying to hit something in between 0.25 and 0.35 for our DLT rate. Then we're just going to extrapolate that. So rather than lumping the intervals on either side into underdosing and overdosing, we're still going to have those categories, but we're going to create finer detail by creating keys of the same length of the proper dosing interval, in this case 0.1, on either side. So as you can see, for the overdosing side in red, we have 0.35 to 0.45, 0.45, 0.55. So a bunch of these different keys. And I promise I'll show an image just shortly that will probably make this a little bit easier to see. But essentially, we're just making these keys along the entire distribution. And when it gets to the ends, you might notice it's not exactly the same size, but that's fine. It shouldn't influence the design. It's at that point when you're getting close to 1, that's way too toxic anyways. So we hopefully would never be in that realm. Same as with 0, that's fine. That's not a toxic dose. We're probably going to want to be escalating anyways. So we're creating essentially a piano, where it gets the name keyboard design. So A couple of things, all the keys obviously have to be within the range of 0 to 1. We're making the intervals equal length to avoid the non-proportional weights to the MTPI. It's pretty easy to construct because all we need to do is think what we want our target key to be, and then we can populate the rest of the keys based off the interval of that key. Once again, it's a model-assisted design. We know before we even start the trial what our decision-making framework is. As you can see, this table kind of shows an example. Once again, we're using a DLT target of 20% or 30%, where you can notice, if you saw the Boeing talk, this design has the ability to apply your decisions on a per patient basis. So you can see at the top row here, we have 1 to 18 patients. So we can either choose to escalate or de-escalate based off of the number of DLTs we have. So as you can see, say we have 3 patients. If there's no DLTs, we're going to escalate. Or if there's 1 DLT, we'll de-escalate in the case of target toxicity of 20%. Whereas if we go to 30%, we're going to de-escalate if there's 2 patients that had a DLT. So like the MTPI before, there's a couple other things that we can do to make this design a little more nifty in terms of safety. We're going to make sure that we eliminate higher doses when we've identified a lower dose to be overly toxic. So say we're at the 3rd dose, we say eliminate that final row. If we have more DLTs at that point, we're just going to get rid of the upper doses. We're not even going to think of going that direction. And then similarly, we're also going to implement a rule that says you have to treat at least 3 patients before you can eliminate a dose. And the reason being is, you know, what happens if we're starting a trial and our first patient has a DLT? Well, according to this table, we should de-escalate, but we don't have any dose to de-escalate to. This just prevents us from having kind of some confusion and not knowing exactly what to do. We need to look at least 3 patients before we eliminate the dose, and we need to figure out what's going on before we make any presumptive decisions. So, like very similar to the MTPI, the decision rules are based off of where we are on this distribution. So given the observed data at the current dose, we're going to identify what the strongest key is that has the highest posterior probability. And if that key is left of our target, we're going to escalate. If our key is right of our target MTD, that range, we're going to de-escalate. And if the target key is the strongest key, we're going to remain. So it's a lot easier to tell what's going on if we look at it visually. So graphically, the strongest key is going to be the one with the largest area under the posterior distribution curve of the DLT rate of the current dose. So you can see in this image, we have de-escalation, escalation, and stay, and what our curve is going to look like. And so the statistical rationale is pretty straightforward. The strong key represents where the true DLT rate of the current dose is most likely located. So if the strongest key is on the left side of the target key, that means the observed data is suggesting that the current dose is most likely to represent underdosing. And so de-escalation is needed. Escalation is needed. So if the strongest key is the target key, then the observed data supports the idea that the current dose is most likely to be the proper dosing interval. And thus it's desirable to retain the current dose for treating the next patient. So basically we're just formulating these curves as we go along based on the observed data. And we can see, well, this dose that we're at, for instance, is too toxic. We're most likely residing in the density to the right of the curve per se. That means that we need to de-escalate and so on. If it's too large or it's to the left, we need to escalate. It's very conceptually, it's pretty easy to understand. And now you can see it has those equal lengths too. So we're not just looking at this huge range of possibilities in terms of de-escalation. We can be a little finer in determining where we're at and what we should be doing. So I think it's pretty clear the keyboard design has a lot of benefits, especially relative to the MTPI. It's going to yield much better overdose control and give us higher accuracy in terms of identifying the true MTD. And as I mentioned before, the keyboard design has some additional safety constraints built in. Mentioned there's the dose elimination rule. So if your observed data indicates that there's more than 95% chance that the current dose is above MTD, it's eliminated. And like I said, if there's doses above that, those are eliminated as well. As is just to prevent overly toxic doses from being included in the further decision making. We don't even have to consider those anymore. We know they're too toxic. If the first dose is eliminated, we're just going to terminate the trial early because we know right off the bat the drug is too toxic. We don't have to do any exploration or look at any other doses. And like I mentioned, because of the possibility of being able to make our decisions on a patient per patient basis, we are still building in the fact that you need to look at enough data to really truly be able to make that decision. So before you eliminate a dose, you have to at least have 3 patients being treated at that dose. Like I said, that can eliminate, for example, a case where you have the possibility of having a DLT with your first patient, which can make things a little bit confusing. So in practice, it basically follows these 4 steps. We're going to start the trial by treating the first patient, or if we choose to do it in cohorts at the lowest dose, we're going to make our escalation, de-escalation decision based on the pre-tabulated rules, just like 3 + 3. We're going to keep repeating step 2 until the pre-specified maximum sample size is reached, which is another benefit of the keyboard design is we can choose what our sample size has to be before we even start the trial, or we're going to terminate the trial due to safety. And then finally, once we have all the observed data, we can select our MTD using isotonic regression, where isotonic regression just operates by first identifying the doses where the dose toxicity, monotoxicity assumption is violated, and then adjusting for the DLT estimate of these violators such that the final estimate of the DLT rate increases with the dose. So essentially, like I said, just applying the thought that as a dose increases, it's going to get more toxic, but it's also going to get have a higher efficacy, hopefully. So now I've told you that it's better than the 3 + 3, but let's look at in practice how this operates differently and hopefully convince you further that this is a superior design. So first, let's consider a trial. I've shown you this table before where we're looking at 5 doses that we're aiming to find an MTD with a DLT rate of 30%. So the second half of the table. So this figure right here kind of illustrates what would happen if we go line and accrue patients. So first, we're going to start with a cohort of 3. In this case, all 3 of them didn't have a DLT. So based off of this, looking at our table, we have 0 DLTs with 3 patients. So we're going to escalate. So at level 2, once again, we have three more patients. none of them have a DLT. We can even go further and say, what if one of these patients is not evaluable for a DLT because it progressed rapidly, or they refused treatment and didn't receive the treatment for the DLT evaluation period? We can still make our decision, which is great. Because if we had the 3+3 design, we wouldn't know what to do. Whereas here, now we have 2 patients at that dose level. So we can, and none of them experience a DLT, so we can still escalate and continue going. So then now we're at the 3rd dose level. We're going to treat 3 patients. 2 of them have a DLT. By our decision table, we're going to drop down back to level 2. 3 more patients there with no DLTs. Now we have 5 evaluable patients with no DLTs. Pretty easy to figure out what we're going to do, which is we're going to escalate back to level 3. So now we're getting into having more patients. We're in our 5th cohort. Once again, we enroll 3 patients. They don't have DLTs, but we need to consider that we had a cohort treated at this level already. So now we're sitting at 6 patients, 2 of them having a DLT, which means that we're going to stay now because we don't have. If you look at the table, you can see we would de-escalate if there's 3 patients or more. Escalate if there's 1 patient more. So we're right in there, we're going to stay. So we'll treat 3 more patients. Once again, we don't have an evaluable patient for whatever reason, which is fine because now we just have 8 patients and we can still use our table, determine to stay. Then the next 2 cohorts enroll where we have DLT and another non-evaluable patient. And we're still just fine. We can keep using our table and we keep electing to stay until finally we've reached this last cohort here. We're about excuse me, 8 cohorts in, and we have and we're going to make the decision at this point to escalate. Where immediately we have 2 DLTs and 1 patient without. We're at a new dose now, so we're going to look back at our what action we should take for 3 patients. 2 DLTs of 3 patients, we're going to de-escalate. We hit our 3rd dose, and this is where us having a pre-specified sample size helps. We've hit, we're going to hit our maximum sample size of 30 patients reached. And at this point, we're going to choose based off of all of our information, dose 3 as the MTD, because our estimated DLT rate is 26.7% using all the information that we've collected, which is quite close to our DLT target of 30%. So you can see, if we were just doing the 3+3, we would have already stopped by the fourth cohort, because we would have gone to dose 3, hit 2 DLTs, immediately de-escalated to dose 2, which would mean that the 3+3 would be choosing a dose that's subtherapeutic, just based off of 3 patients. Whereas now with the keyboard design, we're picking the better dose, and we're getting and ultimately we're going to get a better estimate because we have so many patients enrolled at that dose to feed information into our phase 2 trial. Whereas oops. All right. So just in that simple example, we can already see a lot of the benefits for the keyboard design relative to the 3+3. So we can target any pre-specified DLT rate, which is something I talked about in my first lecture. The 3+3 design really restricts us to a range of 17% to 33% DLT rate. And we're somewhere in that window, but we don't know exactly where, and we can't really choose where we want to be within that. And this is great because sometimes we may want to target a higher DLT rate, like 30% for cancers that don't really have an effective treatment available, and we're fine tolerating a little more toxicity. Another great benefit over the 3+3 is, in the example, I chose to use cohorts of 3, but that doesn't need to be the case. You can rely on any number of cohorts. We can even go on a per patient basis because we have that decision table that shows us exactly what to do for each number of patients that we have for the dose. And then unlike the 3+3, we can also pre-specify what our sample size is. So basically, it allows the user to choose an appropriate sample size to achieve whatever desirable operating characteristics you want. So if we want to achieve a certain MTD accuracy, have a 95% confidence interval of a certain size, we can do that. We can say, we're going to treat 30 patients or whatever. So ultimately, our MTD should hopefully have a pretty good estimate going into our phase 2 trial, which is great. We want as much information as possible. We don't want to be treating patients at a subtherapeutic dose because we don't want to find that out later and have to try to modify something, because that's just a waste of time. We want as much information and the best information we can get in our phase 1 design. So now that I've kind of told you and shown you an example of why it's better than 3+3, just if you need a little extra convincing, let's look at a little simulation that shows how this works in practice. So, as an example to demonstrate performance, I'm going to present the results of a computer simulation, which actually came from the paper on the keyboard design, but I think it's a really good example. What they did is they compared the MTPI, the 3+3, and the keyboard. So what this demonstration has is they're going to choose 5 different dose levels, and they're going to shoot for a maximum sample size of 30 for the MTPI, or excuse me, for the keyboard design, MTPI and 3+3 don't allow you to do that. They're going to target DLT rates of 20% and 30% to show the differences there. Remember, though, the 3+3 isn't really able to distinguish between these two cases. So this really kind of is going to highlight how the keyboard design performs so much better relative to the 3+3 in that aspect. For the MTPI and the keyboard design, they're going to choose a proper dosing interval of 15% to 23% for the target DLT rate of 20%. And then 25 to 35% for the target rate of 30% respectively. They're good. So what they did is they took 10 different toxicity scenarios, which I have in this figure right here. You can see what they did is they made it so the DLT rate increases monotonically, like I said. That dotted line in this case is going to represent our target MTD, which for this particular figure is 20%. Each of those boxes represents the dose level. So as you can see, I know there's not numbers on this plot, but the first 2 scenarios are actually going to be of the 10, saying the MTD is the very first dose, whereas scenarios 9 and 10 are going to say the MTD is this last dose 5. So when they do the simulation, they're going to run 10,000 trials. So it's going to get us a lot of good information. And just something else to kind of know, when they did the simulation, they actually used cohorts of size 1 for the MTPI and keyboard design, just to illustrate the potential of that, which in practice, it's not really showing us a whole lot in our results, but it's a really neat thing that you can do. So anyways, sorry, just throw a little more information at you. We're going to be looking at a few different 4 different metrics then to compare performance, which the first being the percentage of correct selection, or the PCS. So we want to see what the accuracy of these designs are relative to each other. And this is just defined as the percentage of times that the MTD is correctly selected in the 10,000 trials. And we're going to look at the average percentage of patients treated at the MTD across 10,000 simulated trials. Because what we want is we want to be accurate, and we also want to be putting as many patients as we can in that MTD, because that's going to give us a good estimate then of what our DLT rate is in terms of our 95% confidence intervals, and then also, give us a little bit of a start of an idea, maybe what our efficacy could be in terms of our exploratory analysis. Then we're also going to look at the average percentage of patients treated above the MTD across 10,000 simulated trials, basically saying, are we treating people at doses that are too toxic? And how many are we treating? And then just as a part of that, another safety thing, the risk of overdosing. So we're going to look at the percentage of simulated trials in which a large percent of patients are treated at doses above the MTD. So in other words, given a trial, this metric is going to quantify how likely a design is to overdose X% of the patients. And in this case, we're going to look at 60 and 80%. So now that I've thrown a lot of words at you, let's look at what these results actually are. So this first image is talking about correct selection. So that first metric I talked about. So we look at the percentage of the correct selection for the MTD. So the thing that should stick out immediately is the 3+3 performs pretty badly. Most of the time, it's below 40% in terms of selecting the MTD. And it really only gets above 40% when we're starting to looking at scenarios 9 and 10, when that last dose is our MTD. We've gone through everything. And the other thing to note, the MTPI, actually it doesn't seem to perform that much better than the 3+3. Kind of bounces in and out in terms of the correct selection. But look at our keyboard design. That is consistently performing better than both the MTPI and the 3+3 in terms of choosing the correct MTD. And notice, well, there is some variation just because of the simulations. This is consistent for both the target DLT rate of 20% and 30%. And this is great because our keyboard design is getting us close to what we want our target DLT to be, whereas the 3+3, we don't know. It's going to be somewhere between 17 and 33%. Like I said, another metric of success in an accurate trial is assigning the most patients that we can to the MTD. So once again, looking at that blue line, we can see that the blue and red line, we can see the MTPI and the keyboard design perform the best overall, looking at figures A here. However, the 3+3 design initially performs great. Look at that, 70%, or excuse me, 70% of the patients are being treated at the MTD for those first two scenarios. Remember, those first two scenarios are just where that first dose is our MTD. So of course it's gonna have the most patients allocated to that, because it's probably just gonna go 3 patients first dose, 3 patients second dose, overly toxic, let's just jump back to the first dose, and then boom. But you can see as we go along in those doses saying that higher doses are going to be the MTD, 3+3 just doesn't do that great. By the time we hit scenarios 9 and 10, where the 5th dose is our MTD, that's a huge difference there, where the keyboard and MTPI are putting more patients at the MTD, where the 3+3, I mean, you've had to go through all those different levels, and you're only putting 6 patients at your MTD, which isn't great for our estimation later. So, excuse me. Conversely, though, when we look at our average number of patients treated above the MTD, this is where the 3+3 is having better metrics in this figure B. We can see that across all the scenarios, until we hit the last, which has the highest dose being the MTD. The 3+3 has less patients treated above the MTD. But like I said, this is just due to the feature of the design. We have a smaller sample size. We're not really exploring the dose levels that much. The 3+3 then will have just less patients above the MTD because we're not really exploring the dose space that much. And also, that means then we have a less chance of truly finding it because as we saw in my example prior, it's just too conservative. It's going to jump down right away. It's not really going to explore the dose space that much. We're not throwing that many patients at it. We're not getting a really good estimate. But, we also need to take into consideration overdosing, which looking at the risk of overdosing, I have two different scenarios here, figures A and B, which is the risk of overdosing 60% or more patients in A, or the risk of overdosing 80% or more patients in figure B. Excuse me. The keyboard and 3+3 here are actually performing very comparably. So while the keyboard might be treating more patients above the MTD, the actual risk of overdosing is pretty comparable to the 3+3. And always, as we can see, the MTPI, due to that issue I'd point out earlier in terms of the overdosing interval, we're going to have a substantially higher risk across all the scenarios of the overdosing more patients, except for the last two scenarios where we're just hitting the MTD at dose level 5. So once again, while the 3+3 itself has a lower risk of overdosing, this is just a product of being overly conservative, which means it will have lower accuracy to actually identify the MTD. Whereas the keyboard design really achieves that good balance between safety and identifying the MTD. Excuse me. So for those of you that attended last talk and talking about the Boyne, you might be wondering, what's the difference between the keyboard design and the Boyne? Well, statistically, in the keyboard design, we're just looking at posterior distributions and toxicity to make escalation decisions. Whereas in the Boyne, we're looking at the observed toxicity rate for escalation decisions. In terms of operation, for the keyboard, we're going to compare the number of DLTs observed at the current dose with escalation boundaries that vary according to the number of patients treated. Whereas in Boyne, we're going to compare the observed toxicity rate with a pair of fixed escalation cutoffs. So ultimately, this boils down to the Boyne itself is probably a little bit simpler in practice, but both of these designs yield very similar operating characteristics. So ultimately, the decision between those two can be based on user preference. Excuse me. So in conclusion, I'd really highly recommend this keyboard design, and same as the Boyne design. Both these designs are great. They perform better than the 3+3. They're very easy to implement, and they have a higher precision to correctly select MTD. So just a little plug for our group at the BBSR. We're more than happy to help you design your phase 1 trial using the keyboard design, Boyne, or any other similarly appropriate design. And Cancer Center helps support our efforts. So all that consultation to design your trial is free. Obviously, we also provide other services in terms of grant writing, manuscript preparation, and so on. Next week, my colleague, Dr. Hugh, is going to talk about the continual reassessment method, or the CRM, as I mentioned, which is a model-based design, different than these model-assisted designs. It's more powerful in some ways, but it also has some drawbacks because of that. And hopefully you all can make that talk. I know I didn't leave a ton of time left, but if there's any questions, happy to try to answer them now. Perfect. I guess if there's no questions, I'll end the talk here. Thank you all for attending. Like I said, this should be posted to YouTube if you want to refer to it later, or always feel free to email us or reach out if you have any questions. And I hope all of you have a good day.